Hello, everyone. Hi. All right, so we're going to get started. As you guys probably saw on the schedule, this workshop is 2 hours, and that's because there's like a lot of content to cover. So I think we're just going to get right into it. Welcome to the machine learning workshop. This is the beginner ML workshop. So I posted a big long message in Slack. We have 3 different ML workshops, and I was trying to kind of break down what your experience level should be for each of them. But this is the beginner one, so like you don't actually need any experience. As long as you can do algebra, like y equals mx plus b, I think is the most complicated equation I have in this slideshow. So, all right, is everyone good with that? We're gonna get started. Sick. So, yeah, prerequisites for this workshop: high school algebra, and a little bit of basic Python. And then also, we're gonna ask that you guys install Python 3.7 so that you can run some of the code that we're gonna do at the very end. But we'll, if you don't have it installed, we can help you. Like we have, other instructors here to help you. We'll go around and help you guys out as we get to that portion of like the activities. And then we have a GitHub repo with like starter code, so you will need to know how to get the code from the GitHub repo. Again, we can help you if you get stuck. Okay. Cool. So we're gonna give a quick overview of what we're gonna cover in this workshop. Right? And so kind of the first things we want to do are tell you what is machine learning, like what the hell are we actually doing here, how to then kind of look at your data, because the most important part about machine learning, honestly, is data. And it's the whole point of machine learning is to analyze data. So we're going to talk about data, and then we're going to talk about a couple different models. So the idea today is to talk about 4, maybe 3, depending on how you slice it, 3 to 4 models. The first one is going to be linear models. And then after that, we're going to talk about some data transformations. And then we're going to jump into higher order functions, which is just like a fancy way for saying fancy linear models. And then KNearest Neighbors. And finally, we'll talk about decision trees. And then at the very end, we're going to actually like deploy a model that you've trained to like a thing that you can use. All right, we're going to make a website. It's pretty exciting. Like that's what the starter code is for. So it should be good. Making ML web scale. All right, so let's jump right into it. What is machine learning? And I'm gonna ask that maybe you guys participate in this. Like, what do you think machine learning is? Does anybody want to volunteer? I don't know, a guess or a thought of what you think machine learning is? Anyone? Yes.
I feel like it's the study of algorithms and statistical models.
Okay. The study of algorithms and models. Okay. Anyone else? Anyone? All right.
It's the study of robot brains.
Robot brains? Okay. Cool. Yeah. So, we think that I'm the one who came up with this definition, I think, right? So this is what I put up on the slide. It's basically that we want to talk about algorithms that allow us to analyze data. The big thing here is data. And the word data is not actually on this slide anywhere, but statistical models is the key thing that like means data, right? And the idea here is that a statistical model, like, right, that sounds like a really fancy word, and it's not actually a fancy word at all. A statistical model is literally just a function. So, like, if you know what y equals mx plus b is, that's a statistical model. And we're going to talk about it next. So, yeah, we'll get into it. When should you use machine learning? Some people may tell you, like, just always use machine learning. That's wrong. You should, like, not do that. And if you do that, you are wrong. So don't do that. But what you should do is you should use machine learning when you have a problem that is well suited to machine learning, right? It is a problem where you don't have an explicit solution for every situation. It's a problem where rules that are kind of fixed aren't really good, and you might want to have some more flexibility based on the inputs that you get and the outputs that you want. So some of these kind of tasks here, like handwriting recognition and translating from one language to another, these tasks are really well suited to machine learning. And machine learning methods have done better and better as time goes on than traditional algorithms have at these tasks. So, yeah. All right, so we're going to start off by talking kind of about like the 2 main paradigms of machine learning, okay? And the first one is called supervised learning. Wow, my speaker notes like just blacked out here. But all right, so the idea of supervised learning is that you want to approximate functions from some kind of input and output pair. Okay, and that means that you have the input and you have the output, and you want to try and guess what function maps from that input to that output. And so, to kind of maybe more broadly discuss what kind of algorithm you might use when you're doing supervised learning, right? You might have a training portion, and then you might have a testing portion. And in the training portion, you provide to your model the input that you want to use as your input, and then also the correct output that corresponds with it. Okay, this is really important. You provide the correct output, and then you tell the model, hey, this is the input, and this is the output I want you to get. I want you to try and get it, and make some model that does that the best, and that's training. And as you start doing that better and better, your model will get trained, and then afterwards, you'll go to the testing step, where you, again, have input and output pairs, but this time, you don't give the correct output to the model. You tell it, here's an input, guess what the output would be, and then you, the human, check whether or not it's close. And if it's good, then your model obviously is performing well, and if it's not, then your model's not performing well. And we call that accuracy. And that's basically the measure that machine learning is trying to improve. You're trying to improve your accuracy. You're always trying to do better on this metric. Some measure of goodness that tells you how well you're mapping your inputs to the correct outputs. And that's basically the key concept of supervised learning. You can see here, I have these two graphs. There's two kind of subtasks within supervised learning. It's called regression and classification. Again, big words, doesn't actually mean much in practice. The difference between these two is very minimal. But you can think about it as what you kind of want to do with your data. So regression is when you have a thing of data and you kind of want to predict more of that data, given some input. Whereas classification is you have some data and you want to split it up into different classes or kind of subsets of the data. But in reality, the algorithms used for both of these are very, very similar. And in practice, there's not very much difference. So we just call it all supervised learning. Okay. So next up, we have unsupervised learning. And we're not going to talk too much about unsupervised learning today because none of the algorithms we're going to cover really are unsupervised learning. But the idea is that with unsupervised learning, you don't really have a specific output. You don't know the correct answer for the output. You just kind of have some input data, and there could be some pattern there when you don't know what the pattern is. So the idea is that you kind of want to ask the model that you're training to find some pattern. Find me the pattern that could be in this data, and tell me what it is, and that may help you understand your data. Right? This is something you do when you really don't know too much about your data and you want to understand more. And so on this slide, we have an algorithm called clustering. And the way clustering works is, again, you have some input points. They're all blue. And, they're data that belongs to some thing, right? It could be it could represent anything. But what you want to find out is, within the stuff that's represented in this data, are there some broader categories? Or is there some pattern that I am missing? And so you can see, on the right, after you apply the clustering algorithm, it tells you, hey, the data that's all yellow, it's like other data that's also yellow, and we call that a cluster. Yes, question?
What's the difference between this and supervised classification?
And supervised classification. That's a good question. There's actually not a ton of difference, but the key one is that, again, in unsupervised learning, you don't actually know what the correct cluster should be. In supervised classification, you are aware of the correct class. So when you're training your model, you tell it, hey, I know that these data points belong together, and you make sure that it groups them together. You want to try and group them together because you know the correct grouping. Whereas in unsupervised learning, you don't know the correct grouping ahead of time. There is no correct answer. There's just some pattern.
Yeah, one way you could think about it is if for supervised learning, you have a test set where you don't know the true labels for any of the points, and you have a training set where you do. And so unsupervised learning is everything is in the test set, basically. So the algorithms you need to use are going to be completely different.
Yeah. But that was a really good question. Okay. Sick. So we're going to start off. We're going to talk about linear regression. So, what is linear regression? I mean, honestly, it's exactly what you think it is, right? If you're like looking at that and you're like, yo, that's a line, y equals mx plus b, bingo, you got it, all right? You all are like step one into machine learning. That's basically all there is to it. There's a line, there's an equation that tells you what that line is, and your job is to like find the line that best represents the data, right? And in this case, right, we have some data here about my grumpiness and the amount of sleep I've gotten. I can tell you that in the last day I've gotten 0, so you should kind of guess where I'm at there. You know, and the trend here is represented by that blue line. So, you know, that's a model that's estimating, you know, let's say you had a new data point where you don't know how grumpy Shane is, but you do know how much sleep he had last night. You
4
might be,
hours, by the way.
you might be able to go onto that line and be like, where is 4? It's not even on the graph, Shane. But whatever. So you can see that Shane's grumpiness level, you know, it's pretty high, even though he got less sleep. All right, yeah, whatever. So how do we do this? Like, what's a little bit more detail of how we do linear regression, right? Like I just said, fit a line, but you can't just like plot your data and draw a line. I mean, you can, but then that's not machine learning. That's like human learning. You're the one learning the algorithm. That's pointless. We want the computer to learn the algorithm. So if we want the computer to learn the algorithm, we have to tell it what is the best line. And computers can only think in numbers. They can't read our minds. So you have to tell the computer what is the number that best represents the best line. And that means we have to kind of quantify best. We have to figure out what does it mean to be good for a line. As it relates to data. And so I kind of want to ask you guys, I've given you a hint in the picture, but how can you compute that your linear model, right, is good? And how can we kind of quantify that? Like what does it mean to be a good line? Does anybody have an idea? Yeah.
Your line wants to be, for example, in this example, is equally far from points that are above the line and points that are below the line.
Okay, yeah, that's a really good idea. That's a good thought. I like that.
The sum of the square of the residuals should be the smallest.
Oh, okay, all right, cool. We got some fancy math words here. I like it. Yeah. So that's basically it in math terms. But why don't you try throwing that out in English for like everyone else?
Yeah, pretty much you want the residual is the distance between the point and the proposed line.
Yeah.
And you want the sum of the square of all of those distances to be the smallest.
Okay, yeah, that's exactly right. That's exactly right. So basically what he's saying, right, for those of us who are not super math inclined, is that there's this green line that goes between the red point and the blue line, okay? And that green line is basically just your distance between your point and your line. And what you want to do is make sure that all those distances are as small as possible. So your line is like as close to the points as they can be. And so, yeah, you know, as he said, that's we square it and we take the average. And so you may have noticed in the title I said don't be mean to squares, and that's because this metric of goodness is called mean squared error. So we're going to talk about it next. It's the sum of squared errors. So this is a formula. It might look scary, but it's really not too bad. The kind of big E looking thing is just the summation. So that means that you take the sum of everything to your right, my left, okay? Everything to the right, you take the sum of that stuff repeatedly, and it's like a for loop. So if you see the I at the bottom, the I starts at 1, and it goes to n. It's just a for loop, and you add all the things inside the for loop. That's it. And then on the inside, you have the predicted value, you have the real value, you subtract them, and you square it. Okay? Any questions? No? Pretty straightforward, hopefully? Cool. All right, and then obviously this is just the sum. There's one part missing. Anybody know what's missing from this? Anyone? I'll give you a hint. It was on the title of the last slide.
Divided by the number of points.
Yes, bingo, that's right. So this is just the sum. It's not actually the mean. So in order to get the mean, you have to divide this by n. So it would just be 1 over n on the outside. You just multiply it by that. Yeah. So, all right, can anybody tell me why we're squaring the difference? Anyone? Any guesses? Why are we squaring it? Yes.
To get rid of negative values.
Bingo. Why do we want to get rid of the negative values?
Otherwise, you might have a zero error if you have like positive 100, negative 100.
Yes, that's exactly right. So to kind of get at why you want to do that, you'll notice that some of the green lines, right, they're pointing up and some of them are pointing down. And so if you were to just kind of subtract the y values there, subtract the y value like maybe for 6 and minus 5, right? That's a positive one. And then you subtract the 5 from the 6, and then you get a negative 1, and now it cancels out. And if you do that, then basically your points can be arbitrarily far away, right? They could be minus 100 and plus 100 away from your line, and then your computer is going to think that's a great line, even though it's really far away from the points. So in order to solve that problem, really you can do two things. You can take the absolute value, or you can square it, and it doesn't really make too much of a difference. There's some like mathematical reasons why you might choose one over the other, but honestly, we're not going to worry about it too much for now. The idea is just that you take the square, and it gets rid of the negatives, so you can add them all up together, and then that means that all of your errors, right, the distance between the line that you're predicting and the real points of data, you're adding up all those distances in like a positive manner, so that the farther away they get, the higher your error gets. And that's telling you how bad. The higher the error is, the more bad your line is. And the lower the error is, the better your line is, the higher your accuracy is. So, all right, I'm gonna not go. Does anybody have questions before I go on to the next thing? Because I'm moving kind of fast. So, apologize. No? Okay, cool. So that was hopefully pretty easy. It was just like lines and stuff. And we're gonna kind of turn it up a little notch because that's not the interesting machine learning you guys came here to learn about, probably. Maybe you did, I don't know. Yeah. Does anybody kind of know what's wrong with this data set, given like the previous models that we've been using? The only one model that we know about so far? Like, what's kind of wrong with this? Yeah. Yeah, the distribution's kind of bad. And you think you could fit a line to this? I mean, actually, you kind of can, yeah, because those points up there shouldn't be like that in that direction. But you could fit a line to this. It would just kind of suck. And the reason it would kind of suck is because you have a ton of points in the bottom corner, and it doesn't really look like, you know, if you drew a line through this, yeah, you would get the points on the top, and everything would kind of be equidistant, but you know, it wouldn't necessarily be a good prediction, because as you started getting into the higher body weights on that bottom x-axis, you're not really, the trend is less obvious because there's not a lot of data points there. So you really could be hit or miss. And so when you have this kind of problem, right, a linear model is just not going to cut it. Like, we have data in the real world that's not a line. You see it every day. You throw a ball in the air and it's not a line. You can't model that with a line. No matter what you do, you just can't use a line for everything. So we're going to have to step it up a notch. And what we're going to do is bend the data. And so the way we're going to do that is by using the logarithm function. So for, you know, logarithm function, hopefully everyone's familiar with it. I'm not going to explain it. Yeah? Cool. So basically what you do is you take your data that was there, and it looks kind of gross, and then you apply the logarithm to all the data. And then you get different data. But now it's on a log scale. Like, you'll notice the x and y axes are different. And that's because we've actually just changed the data. And when we do that, we get a different kind of distribution and also data that's kind of more linear, right? It definitely looks more like a line than it did before. And you can definitely fit a line to this new data. Like, you guys all agree with me there? It would be really easy to fit a linear model to that new logged data, right? After you apply the logarithm transformation. And basically, the idea is that this kind of method, right, is one just specific example of a general method that we can use when we want to fit a linear model or use a linear model on data that's not really linear. You can kind of think about this in two ways. The one way you can think about it is you have applied some transformation to the data that makes it linear, and then you can fit a linear model. And the other way you can think about it, and this is like the second way is kind of what's commonly thought about when people, when people talk about like fitting some of these more complicated linear regression models is what you're really doing is you're not really transforming the data, because like that's not necessarily a good way to think about it. What you're actually doing is you're finding a linear function that when it's combined with the log gets you the original data. And that's kind of a weird way of thinking about it, but it's a linear function, right, that when you nest it with a log function gives you what that original data looked like. And so the thing you're learning is linear, but the end result, it's not linear at all, because you've applied something else on top of it. It's like a nested function, right? You're doing one inside the other. And this is really powerful. I'm not gonna like get into all the math and boring details about how it works, but the idea is that you can use a linear method to learn nonlinear functions for anything, like really, really complicated stuff. And if you ever heard of like a support vector machine, this is exactly how they work. It's really just a linear method. It's using linear math, but there's some other functions applied on top of it that make it nonlinear and allow you to kind of better fit data that isn't linear. And this is really powerful. Like up until I think 2012 or so, maybe a little earlier, maybe like 2006. I don't know. And within the last like 10 years, right? Support vector machines were like the best. That was like the state of the art that we had. Yes, question.
So can you only apply log transform to get that linear graphing right if your original graph is exponential?
Yes, and that is a good point. I kind of glossed over that. You can only really apply this if your original data has some structure that you can take advantage of. But that's for the specific case of the log transformation. When I'm talking it more generally, like that was the log transformation. But in the more general case, if you want to apply other nonlinear functions that you nest with the linear function, they don't have to be the log function. And so your original data can look different, right? Maybe if you wanted to learn, wow, this is gonna, all right, I'm gonna gloss over math here, but let's like pretend for a second you wanted to learn like a parabolic function, right? Something with like an x squared in it. So maybe instead of applying the log transform, you apply an x squared. And like this is not exactly how you'd mathematically do it, but just kind of think about it as you nesting an x squared with a linear function. So now when you combine these two things together, the linear function is just like some weights on the parameters of your x squared plus x plus c, kind of ax squared plus bx plus c, quadratic, right? Your normal quadratic. And the linear function is telling you some like additional weights on top of that. And that is what allows you to learn nonlinear functions using the linear regression methods. Does that kind of make sense? All right, now I'm going to throw something out there for those of you who I know are in Comp Sci like 589 and have an exam on Monday. This is exactly what is called basis expansion. So if you were in class and you were like talking about basis expansion and then you got confused, what I just explained is basis expansion. And a log transform is just one type of basis expansion. And you guys talked about more complicated ones that I'm not going to get into. Okay? Cool? Any questions? Wow, we're going through this super fast. Okay.
More time for the activity.
Yeah, true. Oh, cool. All right. So that's kind of all we've got for linear models, and that's like the most basic kind of model, but it's really powerful, especially when you apply these nonlinear transformations. It can be very, very powerful. And like I said, with the support vector machines, that's kind of a method that was state of the art for a very long time until neural networks and other methods kind of overtook it. So the TLDR of linear models is that they're kind of easy to compute and understand in their basic form, but they don't really do well on all kinds of data because we can't model everything with lines. And so we can make it better. We do some like yucky math, and we can definitely make it better. But that's kind of where we stand. So it doesn't make it more difficult to compute. The math is yucky, so we're not going to talk about it too much, and we're going to move on. All right. So the next model we're going to talk about is KNearest Neighbors. And the way this works, it's pretty simple actually, like really simple. The idea is that you have some data, and you have a thing that you have an input that you want to like predict the output for. And so what you do is you just measure the distance between your input and all the other outputs, and then you find the k closest ones, and you average them all together, and then that's your output. So I'm going to go over that one more time, right? You have an input. You want to find an output for it, estimate one. You don't actually know the real answer. So you want to estimate and guess the output. So you just compute the distance between your input and every other training or data example that you have. And you find the k closest, where k is like some variable, and you just average those k together, and then that is your output. So now that I've said that, I'm going to ask you guys a question. How do you train this model? Does anybody have a guess for how you train it? Yeah.
So would you try several different inputs and then graph them along the outputs to find out the trend of those?
No, but that's an interesting idea. And this is kind of a trick question. Cool. Yes. All right. So that was a trick question, like I said, and the answer is you don't train it because you don't have to. Like the way this model works is the model is the data, right? If you think about it, there's no pre-computation you have to do. The moment you know the input thing that you want to predict, you just compute distances and then you average and then you're done. And there was no parameters to guess. There's no y equals mx plus b. There's no m, there's no b, there's no parameters, there's no math, there's no error. There's none of that crap. You just have the data and the data is your model. Okay? What's up?
So how do you decide k?
That is a great question, and we're going to get there on the next slide. So, yeah, that's the beauty in KNearest Neighbors. Love thy KNN, okay? This is like a super simple model, and it's kind of awesome because of how simple it is. You don't have to train it. That's nuts. So, how do you choose K? And that's a good question, and the answer is kind of in the title of the slide. It's user specified. You choose it. I can't tell you how to pick K. There's not really a formula. You can't just compute K and then this is the K. It's the magic number that works for everything. It doesn't really work like that. But there is some kind of intuition that lets you do a better job for K. And so you guys can kind of look at this picture here, and you'll notice that there's kind of circles with two different K values. And so you're going to notice that if you choose a different K value in this example, you get a different output. And that's kind of sketchy. Think about it for a second, right? You have some input, and you're trying to predict a good output for it, and then you change K, and all of a sudden, you could be wrong now. I mean, I don't know whether the star is supposed to be yellow or purple, but if you knew the right answer, right, in theory, depending on K, you could just get the wrong answer. So it seems like the choice of K is really important. And I just told you that there's no magic formula to compute it either. So this kind of seems like a big knock in the direction of KNearest Neighbors. This is kind of bad. And we're gonna talk about a way to do this better. But for now, just kind of imagine in your head that in order to choose K, maybe the best approach we have is to just try a whole bunch of them and see which ones are good. And that's not a super satisfying answer, and we're going to get into some more nitty-gritty about that in a future slide. But I'm just going to throw some more terminology at you guys for machine learning people. I will get to your question. That, the K is what's called a hyperparameter, and then the whole process, or this dance you do where you try and choose the right value of K, it's called hyperparameter tuning. So you may have heard that or read it somewhere on the internet. And that's basically all it is. It's just choosing this magical K to get you good answers. Yes, you had a question.
Yeah. How would you know what would be the right value for K after trying a bunch?
After trying a bunch? Well, you presumably in this case, you know that the red star is supposed to be something, and you would pick the right value of K by saying can I get the most of my training examples correct? How many of the correct ones can I get with this K? And then if you pick a different K and you get more correct, then maybe that's a better K. But maybe it's not. We're going to talk about the caveats there. But for now, just think of the more stuff you get correct with your model, the better the K is. Okay? All right. Yeah, cool. So we're going to talk about some more caveats with K, I guess, right? We have this example here, and I just want you guys to kind of look at this and just think about it for a second, right? What should the like class of the new observation, that like the black circle thing, right? There's no right answer, but like if you as a human were just to kind of look at this, what do you think it should be? Like, should it be? By the way, that should be an orange square. I don't know why it's gray. That's just like a mistake on the slide. But should it be an orange square or a blue triangle, right? Anyone? What do you think the? All right. How about this? How many of you think that the black dot should be a blue triangle? Raise your hands. Right. It's like basically everyone. How many of you think it should be an orange square? All right, like one person. Nice. So yeah. I mean, we can kind of like look at this and agree that the right classification for a new observation is the blue triangle. But what happens if we set k to 1 here? Like, let's say we just pick k equals 1. What would happen? Anyone? Yeah.
Circle that I would draw would only include that. I'm assuming that that square is distance 1 away from the
Yeah.
black dot.
Yep.
It would only include the square and none of the triangles. And even though there are more triangles around it, because your k is so low, you don't see any of that.
Yeah, no, that's exactly right. So, we all agreed just now that really the best classification was the blue triangle. But if we pick a k value that's bad, right, 1 we're going to say is bad, we're going to get the wrong answer. And this is kind of like similar to what we had on the last slide, but hopefully this example is like more clear, right? And so I'm going to ask you, what happens if we make k like really big? Like, what if I make k 11, right? Because 1's obviously way too small. So let's make it 11. 11 is, I think, yeah, 11. Let's make it 11. What happens? Anyone? What? Yeah.
It's going to take the overall majority vote of all the data.
Yeah, cool. What would that be?
Orange.
Yeah, right. I'm sorry that one's gray. That's like I said, it's a mistake. So it would be orange squares, right? If you took the majority opinion here, you would just get orange square. And that's also wrong. And so it seems like, we can't really win here. Like, we have a low k and we have a high k, and it's all just wrong. So what's like the best approach? And the answer is you kind of have to like get this Goldilocks magic going where you just pick the right k. And that's like not a satisfying answer because, again, you just like pick this middle ground k and then it gets you the right answer. Yes, question.
Could you just take the distance of all the data and, for example, the blue ones have a sort of average distance to the black point, the orange ones have an average distance. Could you just use that and like, because the triangles tend to be closer to the black dot, you could say that.
Yeah, and that's a really good intuition. The algorithm you've just described is not called K-nearest neighbors. That's actually clustering. And so the idea with clustering.
Well, but you can actually do that with KNearest Neighbors.
Oh, you can? Okay.
Yeah. It's like weighted KNearest Neighbors.
Oh,
The problem with what you just said, where you take the average of the distance of all of the triangles with your point and all of the squares with your point, is that if you think about it, you could have some large region of triangles very far away and some large region of squares very far away. And then, though the distribution in that far off corner will tell you what the class is for this. And so sort of you can think, okay, how do I avoid faraway points affecting my weighted average? Well, you just do what K-nearest neighbors does. You set a value k, and then you do a weighted average of the distances of those k points instead of just sort of like picking, the class or averaging. But then you have the same k setting problem.
Right. You still have to pick k. You can't really get around it. Right, and it's not really a good answer here. And so I'm going to leave you with that really unsatisfying answer of there not really being a good answer. And this is kind of one of the really important things that I guess I want to drive home about machine learning. There's going to be people who like tell you that machine learning can solve everything, and those people are wrong. And the reason why those people are wrong is because of this. Because there's like not a good way to determine what's the best. And sometimes we have this ambiguity, and we just kind of have to roll with it. And that's fine. Like, it's not bad, right? Machine learning can still help us solve lots of complicated problems that we couldn't otherwise solve. And the kind of crucial thing here is that the more you understand about how these algorithms work, the reason people get paid a lot of money to do machine learning and like why there's a lot of hype around it is that picking this value for k is like really hard. Obviously not like in this example, but there are bigger data sets and more complicated algorithms where you have these like little parameter things that are really hard to choose. And it's kind of hard to know why you choose a particular one either. And so what it comes down to is you have to really understand both the data and the algorithm that you're using. And that will kind of help you make the best, most educated guess about k or whatever other hyperparameter you're tuning that you can possibly make. And that kind of guessing game and like that intuition, you can only get that intuition by like doing machine learning. You have to like practice it regularly, right? You have to like look at a new data set you've never seen before and a new algorithm that you've never seen before and like try and understand it and make some sense of it. And that will help you choose the right values and kind of do the right things. So sorry if that's a little preachy, but like kind of what I want to drive home for you guys is that, you know, don't get frustrated super quickly when like your model doesn't work or something like that, right? It could be something as stupid as you just like didn't get the right hyperparameter the first time. And you will get it eventually. Like you will eventually get this intuition of, you know, hey, my model is doing this. Maybe this setting I need to tweak it this way. And that kind of intuition, because it's not really a hard science. It's just like you have this gut feeling and you kind of, you fiddle with it. You do this dance with the parameters. And that dance, that's what kind of ML is all about, and I think that's part of the reason why people who are good at it are in really high demand and they get paid a lot of money. So that's just like my little side spiel. Okay? And so we're gonna kind of go deeper into the problem here of K. And we're gonna talk about over and underfitting, which are words you may have heard. And also like you'll see bias and variance, but you should ignore those for now. We'll like get into it later. But like so really clearly as we've demonstrated before, the value of k of this k parameter like matters a lot to the performance of our model. And if we obviously saw that if we set it too high and we set it to 11, right, then we just end up getting this average of like all the points we have, and then we don't actually learn anything, right? So I kind of want you guys to think about it. If in this example we set k to 11, right? Can you see why we wouldn't learn anything? Can anybody like tell me why our model didn't learn anything? Learn in quotes. Yeah.
You'd only be choosing one possible outcome.
Yeah, exactly. You like literally gained 0 new information. You could put anything in, and if k equals 11, you will get the exact same output every single time. So your model has learned literally nothing. And in machine learning circles, we kind of call this kind of aspect of not learning anything, we call it underfitting. And kind of what it means is that you have some data and you're trying to fit a model to it, and underfitting means, underfitting means that you basically like didn't actually fit anything. You just didn't learn anything at all. And that's bad. It's something you want to avoid. And that can happen when your hyperparameters are like tuned incorrectly. You will get underfitting, and you will notice that your model will perform really bad. Right? So you can kind of see this linear model here where it's trying to discriminate between these two classes of points. And the underfit model, right, it clearly just can't differentiate between the red and green points here. And so you know, that's, again, it's this terminology that you will get used to. And you'll have to know, right? So when you go to read about different models, other than the ones we talk about here today, you will read about hyperparameters. And then you'll read that like this hyperparameter, if you increase it, it increases underfitting or it decreases underfitting or something like that. You should know what that means, because that's going to help you, again, play this game of tuning the hyperparameters properly. And so that's underfitting. The other thing, obviously the opposite, is overfitting, right? And so overfitting is like when k equals 1. And again, I'm going to go back to this slide here. K equals 1, and when we overfit, basically it means that we learn too much. Like, how can you learn too much? That seems really counterintuitive. Anybody want to venture a guess for what it means to learn too much, to overfit to the data? Don't we always want to fit to the data? Like, how can you fit too much? Like, you want to. That's the whole point, is fitting to the data set. Yeah, what's up?
Would that kind of be like the opposite of like choosing k equals 11, where now you're only relying on the nearest thing, and so like every time you get an input, it's like a totally different output. You're like, ooh, I discovered something new.
Yeah, that's kind of the right intuition. That's exactly right. So basically, the idea is that there could be some like noise in your data. Like your data is never going to be perfect in the real world, right? When you have a camera, you know, like the lighting could change and you could get some graininess or some other stuff. When you have other like sensors that you use in the real world, they're not perfect. If you're trying to recognize someone's handwriting, you can't expect them to write a perfect 2 every single time. Like it's going to be different just a little bit every single time. And the problem is that when you set K to 1, the model just focuses on the differences, the noise. And you can see here like this kind of the one orange square that's in the circle, it's not close to the other orange squares, right? It's kind of noisy. It doesn't really fall into the category of the other orange squares. Like, I mean, it is an orange square, right? But the data point's a little bit weird. It's inside all the region where all the blue triangles are. And so if you were to just set K equals 1, what might happen is that some of the times you get the answer right, of course. But other times you would just kind of like guess based on some like, you know, random thing that's near you, and that's just wrong. And then your model will also perform poorly in a general case, right? Basically what will happen is your model will be unable to generalize to other data that's outside of the training set. So KNearest Neighbors is kind of like a bad example because we said it doesn't train. But you know, for another model where you do train it, if you overfit, then goodness gracious, sorry, I'm tired. So if you overfit, then what ends up happening is you just like memorize the training data, and then you do really well on the training data, and then when you get something that's different from the training data, your model's just like, I don't know, and you don't want that. Yes.
So it's like you have that line, and if you overfit it, you basically perfect it to imperfection. So
Yes.
when something else happens that has a bit of error, it's
Yes.
because like that second one's pretty generalized. You have a pretty normal continuous pattern throughout your data. And
Exactly
the
right.
last example, it's very like wavy left, right, and it's really bolts of the data. There's no general rule for
Correct.
line.
Yeah.
Yeah. Kind of the best way to think about it is that the data you have was sampled from some population that's unobserved. And if you fit a function to exactly your training data, you're not fitting to the population, you're fitting to the random sample you have of the population. The keyword there is random, right? So if you fit to every single little point, you are literally fitting to like random numbers. That will not help you predict anything in the future.
Yeah, no, that's like exactly the right way to think about it. You can say that you've perfected it to imperfection. I really like that. I'm going to use that in the future. So, yeah. All right. Cool. We're going to talk about a different model now. You can see from the top, it has something to do with trees. And so the next model we're going to talk about is decision trees. So for those of you who are like eco-friendly or whatever, this is your slide. I don't know. I'm tired. So you can see here that we have a linear model, right? And that's the blue line. And the linear model kind of tries to discriminate between these two classes, right? This is a linear classifier. We've got the blue points and the orange points. Sorry for those of you who like might be blue-orange colorblind. I didn't like think about that when I was making these
Blue,
slides.
orange is the colors that people aren't colorblind to. I think
Oh.
you're good.
Stupid. Don't worry about it. All right. So yeah, the blue line tries to discriminate between these 2 points, and it like does a decent job. And then we also have this like jagged kind of black line, and that is the decision tree. And you might be thinking like that doesn't look anything like a tree, and you're right because it doesn't. But the rules that made that line, they do look like a tree, and so I'm going to show those to you right now. And you can kind of see on your right-hand side that the rules here, right? You have some condition. It's very much like in programming, you have some if statements, right? When people say machine learning is just a bunch of if statements, like this is what they're talking about, because this is literally just a bunch of if statements. You have some condition, you check whether it's true or false, yes or no, and then you check a different condition. And when you kind of have this formulation, what you end up creating is like kind of like a piecewise function in math, but a little bit more complicated than that, because it lets you loop around and create these like intricate shapes on your data. And so the reason this is really nice is because these decision tree models, like it's really easy to tell what they're doing, right? Kind of when we were talking about the linear model, and I told you about the logarithmic transformation, right? It might be really hard to visualize in your head what happens when you take a linear model and you apply a log function to it. Like that's, I mean, some of you might be able to visualize that, but I think most of you, myself included, would have some trouble like knowing what the hell is going on with that model. But when you look at a decision tree, especially if you look at the tree version on the right, you can look at that and you know exactly what it's going to do, right? You don't even need to like kind of test it on test data to in your head tell what it's going to output. You can just follow the logic and it makes a lot of sense. And that's why decision trees are really interesting and really popular because they're very interpretable. They're very explainable. You can tell someone how it's working. And this is like the same kind of model, right? It's like a chart that your doctor might use, right? It's a very natural thing for us humans to do, to kind of go through this logical tree. And so the question that I have for you guys is, do you all understand how this model works, by the way? Like, I don't know if I did a good job explaining it. Does it kind of make sense to you? Like, basically each of these conditions is a line that ends at some point and like draws an outline of what the like classifications are for the data. Is that good with everyone? Yeah? All right, cool. So I'm going to ask like maybe a hard question. It's the question that's on the top of the slide actually is, can a tree be too tall? And I don't mean like in real life, but can your tree be too tall? Someone who hasn't answered before. Anyone? No, I'm just going to call him Cole again. All right, Cole.
If it's too tall, you'll get overfitting.
Yeah, that's exactly right. If it's too tall, you're getting an overfitting. Like, why is that? Anyone else? Anyone have a guess? Yes.
Well, if your tree is too tall, that means you're going to have multiple, like even more if statements.
Yeah.
And so if you have even more if statements, then essentially you're just accounting for every single data point, or as many data points as you account for.
Yeah, no, that's exactly right. Like the more if statements you have, the more like data points you're explicitly accounting for. And basically, if you have the same number of if statements as you have data points, then you have literally just replicated the data. Exactly, 100%. So if you just have like 100 data points and you make 100 if statements, then you'll get it right 100% of the time, and you will also have learned literally nothing because you will have overfit. And so that is kind of super important to know. I did say tall, and that was just like a play on words. When we talk about decision trees in machine learning, we don't actually talk about height. We talk about depth. It's because I think it looks like the roots of a tree. I don't know. I didn't name it, but it's called depth, okay? So just to be clear, the hyperparameter that you're tweaking is called depth. And when you increase the depth of your tree, you will overfit more, and or just fit more. And when you decrease the depth of your tree, then you will fit less. And that's will like increase your underfitting and allow you to generalize better to unseen data. Okay? Cool. So the question is, and this is, the question here is should you decide to use a tree? And that question kind of applies for everything we talked about today. Like, should you use K-Nearest Neighbors? Should you use a linear model? Does anyone want to like postulate whether or not you should use these things? No? All right. The answer is going to be, I can't tell you. Like, you should use these things if it makes sense for your data. And that's what this graph down here is really trying to show. You'll see that we have two decision trees, and the data set on the left has very kind of defined boundaries. And it really lends itself to a model like a decision tree because it lets you classify relatively good accuracy and without really having way too many if statements, right? So you're not like overfitting the crap out of this just in order to classify it because there is some pattern. There is something for the tree to learn to latch onto for your model to actually represent, right? Your model is just representing these like 4 rectangles of this graph, right? The 4 rectangular sections, that's all that your model represents. It just takes the square, cuts it up into 4 rectangles, and the model says, hey, this is what I think your data, it falls into one of these 4 boxes. And that's what a classifier does. It takes your data and puts it in a box or a class. And so there is a class to learn with this data set on the left. But with this data set on the right, it's not really lending itself too well to a decision tree, right? It doesn't really look like there's boxes you could really put those points in. So does anybody want to like venture a guess for a model that would do better than the decision tree in this particular data set? Like you could just look at it and guess a model that would like do better of the ones we've talked about. Just like literally the 4 models we have talked about. Clustering. Clustering for the one on the right? No, not so much. The one on the left? Clustering for sure. Yeah, clustering would do awesome. I mean, clustering is like very similar, honestly, to like the decision tree classifier, and that's going to try and like group the stuff together. But not for the one on the right. I think clustering would have difficulty for sure. Yeah.
Things like a linear regression with like yucky logarithms.
Yeah. I mean, honestly, even just a normal linear regression would definitely do better than that KNearest Neighbors. That's a mess, right? But if you just like slapped a line through the middle, you might actually get better. And that's like really simple. So the TLDR here is like, you should look at your data, okay? Like we talked about these models, we talked about some yucky math and some not yucky math, but at the end of the day, no one can tell you what model to use. You have to understand your data. You have to look at your data. You have to think about your data. And that's kind of the hard part. Yes?
Can you go over the 4 different models again?
Yeah, I can definitely repeat them real quick. Yeah. So the 4 different models that we went over a linear model, okay? We went over a log linear model, and then we went over K-nearest neighbors after that, and then decision trees after that. So those are the 4.
You started with clustering.
Oh, and I like briefly mentioned clustering, but we didn't talk about how it works. So, like, I don't really count that. Yes, you had a question over there?
Yeah, so you said you could just slap a line down the middle.
Hmm?
Wouldn't that just be the same as a tree with 1?
Yeah. So kind of.
Not quite.
Not quite. But
Usually when you do a decision tree, your boundaries are going to be on one sort of attribute of the data. So that would be like either the x-axis or the y-axis. So
Yes.
you're picking these vertical lines,
or horizontal lines.
basically.
You
or
can't do a
horizontal
diagonal
lines.
line, right?
So a linear model is going to give you a diagonal line.
Yeah, it could give you a diagonal line. And I would venture to guess, like, I don't know. I'm eyeballing this data, but I think a slightly diagonal line would probably do better on that data. However, like, if we're going to get kind of a little bit interesting with it, I actually tricked you earlier. So this is a tangent, and if you get lost, don't worry about it. But just to answer that question more thoroughly, you're right, and you actually could use a decision tree to learn something that's not a horizontal or vertical line. And I showed it to you earlier on a slide, actually, because I tricked you, and you guys may not have noticed, but this blue line is not a linear model. You can see in the caption it says oblique DT, and that stands for oblique decision tree. And all that is a decision tree that is learning how to split on a boundary that's not the x and y axis. It's a combination of the x and y axis. So it's something you can do, and it's something that people do, but like, sometimes that's very useful. Sometimes it's not. In this case, obviously, it's not very useful because you could just use a linear model. It would like do the same thing. But there are other times where maybe you want to combine some of these diagonals together, and then the oblique decision tree might make a lot of sense, right? Like maybe you can't use boxes, but you need to use hexagons around your data for some reason, right? Like maybe it's beehive data. I don't know. And so that the oblique model will really let you kind of make these strange angles and these diagonals with your decision tree. And so that's a good question, and you absolutely can do that kind of thing with the decision tree. It's not just limited to linear models. Okay, cool. All right, so the next slide here, it's just kind of a recap. And it's really the 2 main takeaways. If you didn't learn anything else from the last hour, and you ignored everything I said, you should just only read this slide and you still will be fine. Because really, when you want to apply machine learning, please look at your data first and try to make some sense of it. Try to think about how your data looks, how your data works, what your data represents, okay? And then you determine some models to try. And even the best machine learning experts can't just pick the right model the first time, or write the best model the first time. That never happens ever in the history of the world. Like, if someone does that, I don't know, they got really lucky, or they're like a genius, and that's weird. So, you know, basically what always happens is you look at your data, and you're like, I think, you know, either K-Nearest Neighbors or decision tree could be pretty good for this, and then you try them both, and you kind of see what happens. And that is basically the essence of machine learning, is that you have to try a bunch of stuff. It's more like experimental than maybe you might be used to with other algorithmic methods in computer science, where you don't really have to try anything, you just implement it, right? Like breadth first search. There's no trial and error in breadth first search. You have a problem, it can be solved with breadth first search, you implement the breadth first search, and then it's solved. And that, like, machine learning really doesn't work that way. And that's kind of like what I want to hammer home. And that's like kind of the really important point here, is that you can't just say like, well, this thing will solve this problem, let me apply the tool, it will solve it, I'm done. It doesn't work like that. It will not work like that, ever. With machine learning, you will have to tweak the hyperparameters. You might have to pick a whole new model. You might be representing your data wrong. Like, maybe you gathered some data and you're like missing a really important data point or feature in the data, and you didn't even account for it, and now your model's like useless in the real world. And that can happen. It happens all the time. And so, you know, the key thing here is the data is important. Understanding the data is important, and like, don't get discouraged if you have to try a whole bunch of different things before it works. Right? And then the last thing, I briefly glossed over this, but you need to choose your hyperparameters carefully. And so, like, if you take CompSci 589, which is like our master's level at UMass, for those of you who are not UMass students, it's the master's level machine learning course, okay? Like, there's a certain professor who teaches it, and he will tell you that if you only learn one thing from that class, and you don't learn anything else, there's really only one thing you need to know, and that is the difference between over and underfitting, right? And how that works. That's it. The trade-off of overfitting versus underfitting, that's like the most important thing in ML. There is nothing more important. If you understand that, you're like well on your way. If you don't understand that, you're going to be lost every single time you read anything related to machine learning, because they will always use the words over and underfitting, and it will always be in reference to hyperparameters, so you like just need to know what that is. And so that's like the other really, really, really important thing from today's kind of lecture thing, talk, whatever, workshop. There we are. All right, so really briefly, questions. Does anybody have questions? Yes?
When you're talking about the decision tree, how do you decide which conditions to use, or what prediction is on?
Yeah, no, that's a really good question, and I totally glossed over it. The reason I glossed over it is because it's like, I don't know. Is it like non-trivial to explain? Do you want to like get into it? I don't know.
I mean, I could get a little bit into it.
Okay, why don't you, Shane? I'll let Shane get a little bit into it. I don't know how much a little bit is. So
The general point of a decision tree is that you have some class of boundaries you could draw, and you know that of that class of boundaries you could draw, one of them is going to give you the sort of best results. And so you will essentially have some kind of like greedy algorithm that just tries a bunch and then picks one and just sticks with it. And you will like pick one feature of the data to split on, find the best one, it'll be pretty fast, and then pick another feature of the data and then find the best one for each of those sections, basically.
And when you say best one?
The one which has the worst classification error, for example. So like if you're classifying apples and oranges, the one which misclassifies the least.
So you're comparing it to your test data.
You're basically trying to come up with a set of boundaries for your test data.
yeah, you're trying to come up with a set of boundaries that like minimize the amount of mistakes you make.
Yeah, and it turns out that there's like algorithmic reasons why you can sort of select them without thinking of all possible combinations. You can select the best first one and then just stick with it, and then just select the best second one, as opposing to having to reason over all possible combinations of two, if that makes sense.
Yeah, the intuition behind this, it's in comp sci we call this greedy algorithm, and like I guess the intuition, again, this is like not technically correct, but the way you might want to think about it is that like in the limit, as you like approach making more and more of these greedy options, you will end up getting like the optimal solution eventually. And like there are ways to prove mathematically that is indeed the case, and that's kind of why we do these boundary picking things the way we do. Because if you were to actually consider every single boundary all at once and not just pick the first best one that you see, or the first like good one that you see, sorry, right? Not best because it's just good. But if you were to try and find the absolute best one at every time step, that would require you to search through the space of like, in this case, right? It's a 10 by 10 thing. So you would have to search 10 squared. You'd have to search 100 different combinations every single time you went through your tree. And that's just like, it's way too much. So your computer will die if you try to do that. And like, as you get to data sets that are bigger and bigger, you quickly realize that it's like computationally impossible. Like even if we had all the computers in the world together computing it, we just couldn't do it. And so that's why we have these like clever little tricks to kind of speed up the optimizations. And that's actually like a good thing to tangent on because we have some time. So like a little thing to tangent on is that another big part of machine learning, and then like what a lot of machine learning research really revolves around is like we have these kind of somewhat simple methods that are just like, you know, counting or like, you know, doing some like really basic math. But you have to do a lot because the whole thing with machine learning is that you have lots and lots of data. And so a lot of the like research and tricks that we do is not necessarily around like doing better models sometimes. Like there's definitely times where we want to do better models, but there's a lot of other research, a lot of other area for improvement in just speeding up existing models or coming up with a clever way to like approximate some computation that if we did it exactly would take forever, but we can get like a good enough guess. And remember, in the world of machine learning, it's not like breadth first search. Good enough is actually good enough because you don't know sometimes what the best is. There is like no clear notion of best because it's a random sample from like this big data. And so if you do the best on the random sample, you just overfit. So like we don't always want to like get the best for our training data, right? We just want to get good enough. And so if you do some approximation on your training data and you get good enough and then you apply that to like the real world, you might actually have a model that does really well. And so that's what I guess that's like an area of research in machine learning and an area that people can go into. So if that's something you're interested in and you like, I guess, coming up with clever, fast algorithms, then like you can also be involved in ML research. It doesn't have to be statistics or you know, data analytics. You can just kind of apply complexity theory to this kind of thing. That's interesting. It's not, I guess, I don't know. You wouldn't normally think of it like that, but that is true, I guess. All right, cool. So that was a tangent. We're gonna do an activity. So grab your laptops, I guess. Okay. And then if you all wanna open Slack and head over to yikes. Okay. And you're gonna head over to this channel that I've created. It's called beginner_ML on Slack. So just like you can just like click on the channels thing and join the Slack channel beginner_ML. All right, and while you're doing that, I'm gonna like get some stuff up on the thing. Oh my god, dude, Colab notebooks are so garbage. And also for this portion, like you only need a web browser. You don't have to install anything yet, so like don't freak out. Okay, just kind of join the Slack channel, and there's a link in there. Okay, you guys should just open that link in a web browser of your choice. I don't normally recommend Chrome, but like if you have Chrome, it will work better in Chrome. It's a Google thing. Like, yeah, I don't know. I don't normally use Chrome, but like we are gonna use it for this because it will work better.
Did you verify if it actually worked yesterday on Chrome? I can take it out.
No, I didn't. Actually, so display settings.
Yeah, like when you have to print PDF out at the end. Yeah.
Alrighty.
No, I know they don't have to. I just mean.
Changes. Okay, cool. So you guys get to like, I'm gonna do it this way so that I can see what I'm doing while I'm showing you all. All right. All right. So hopefully you guys are you're all seeing this thing basically, yeah. Sorry. Beginner_ML. You may have to join it. So what you're gonna want to do here, I'll show you guys actually. If you have Slack open here, okay, you will click on like this channels kind of like thing over here. When you click this, it'll say browse channels, and you can just search begin. Okay, and it's spelled exactly like that, beginner ML. It's called Beginner ML Workshop. The reason I'm doing this is because like otherwise you have to type out that link by hand, and that's really annoying. So this is the best way for me to get it to you all, is via Slack. Right, I'm gonna give you all a minute to do that. I'm gonna get some water, okay? So take your time.
Just talk for like an hour. Yeah. Yeah, you did a good job on the presentation. Did you work on it too? Just type it out. Yeah. I spent more time on it. That's what. We're just gonna stall something like complex. Yeah, that's fair.
How 30?
Get really good. I don't know much. Alright, I'm gonna go then.
Hi. You can't open it.
Each time I click it, this comes up.
Whoa. Yikes. What?
Yeah? Stand here.
Yeah.
Not in the one dark spot.
Oh, I'm sorry. You're fine. Okay, yeah, you could have yelled at me earlier because I had a clicker actually, so I could have just stood here.
No, I didn't want to in case like I didn't want to make you like get distracted. Or something.
No, you should just
You were
told me.
doing a great job.
Thank you. You should have just told me that earlier. What the actual?
I just didn't want to distract.
No.
you, that's all.
Next time, distract me, please. You're not.
Okay.
You're not distracting. What? What? All right. Is anybody else getting like a weird error when they try to open the notebook? Anyone? It's just this person. All right. Interesting.
If you opened it like in private.
Yeah. I mean,
I
give that a
almost
try.
always have it in a private thing.
Oh, also, you're using Edge, dude. This is a Google product. It will like not work in Edge. I love Edge. I use Edge all the
I
time.
don't have any other, so should I?
Yeah, you download Chrome.
Okay.
This thing will like not work in Edge.
Okay.
Yeah, I'm sorry. Yeah. I
use
mean, like you can
Firefox.
open it. You can open it. It just like will lag a whole bunch and be crappy. Google does things. Yeah, I don't know. I feel you though. All right. So I just realized another thing that I'm gonna do for you guys is since you're all in this beginner ML channel, I'm going to put the link to the slides in this channel as well. Okay. So if you guys want to view the slides later, like I'm actually just gonna do it right now. So I'm gonna make a link for the slides. Anyone with a link can view, and I'm going to post it here. Okay, cool. So those are the slides. All of you should be able to view them whenever you like. So there you go. Cool. So I promised you all in the beginning that we would not just talk about machine learning, that we would also do some machine learning. So hopefully this is readable there. It kind of is. All right. Let me know if it's too small. I can make it bigger. Can anyone in the back not see? No, we're good.
I mean, they have it up to, or they should
Yeah,
have it
that's
up
true.
too.
You guys should have that. All right, sick. What's up? Huh? How do you make it dark?
I mean the dark mode.
Ah, the dark. Look, you real programmers over here asking about dark mode right off the bat. So, I love it. Gotta love it. So if you go into preferences here, tools, and then preferences. All right, tools, preferences, and then dark. For those of you who like that dark mode life, okay? Yeah. And actually, while I'm at it, is it easier for you guys to read if I make it in light?
No, it's way harder.
No? Okay. All right. Sometimes the dark mode doesn't cooperate well with the projector, okay? So just wanted to check. We're fine. All right. So I'm gonna kind of try and start from like a very, very low level. So I apologize if some of you are like more familiar with Python and programming. If you are, like, just sit tight, okay? We wanna go at a pace that everyone can understand. So this thing here is called a Jupyter notebook. It used to be called an IPython notebook, which is why the file extension is .ipynb. It literally stands for IPython notebook, right? but we have since it's been renamed to Jupyter Notebooks. That's generally what everyone calls it. And in the machine learning community, people love, and data science actually, data science especially, people love these Jupyter Notebooks. And so they're really, really good for certain things. And those certain things are like, it's really good when you want to quickly, like test some code and like get results that you can see very immediately, without having to like write a main method and like write functions and visualization stuff. This will just kind of like abstract some of that away for you, and it also lets you kind of see what you're doing as you do it, so you can run the code in chunks, and that's kind of what these are. So each one of these blocks is what's called a cell, and you can run each of them individually, and then below the cell, it's going to show you the output of the cell above. Okay? So I have output here because I was testing it out before, so I'm going to try not to spoil it too much for you guys and just delete these.
As you show them all.
Yeah, as I show them all, right? Okay, so yours should look something like this. Wait, hold on. Did I tell them to make a copy or no? Did I just totally mess up?
I don't think you told them to make a copy, but just
Okay, yeah, well, it'll just be in the playground. Okay, so if you want to actually save like what you do here, you should make a copy, because otherwise it will just delete it after, because I don't want you guys editing the thing. So yeah, Kevin is showing you how to do it. What's up?
How to hide that bottom part again of the execution, like the graph and stuff.
How to get it? I'll show you in a minute. Yeah. So just really quickly though, before we get too deep in the weeds, I forgot. You guys should all, after you open this, go to File and hit Save a Copy in Drive. Okay, and that's gonna save a copy of this whole notebook in your Google Drive. And then it's your copy. Any edits you make are yours to keep, and you can open it and look at it whenever you want. Okay? So that's what we're gonna
also
do.
it may be read-only, so you might have to do that.
Right,
just
you
to
might
work
have
on
to
it.
do that because I think I gave you a link that only lets you read it, not edit it. So yeah, you should definitely do this. Like, do it now. All right, I'm gonna give you all like another minute, and then just for File, save a copy in Drive. That's like where it is. And we're gonna give it 30 seconds, and then we're gonna move on. It should open like in a new tab, and it'll call it copy of beginner ML whatever. Right? You can rename it if you want, but like, don't worry about it. All right, so like I was saying, each of these things is called a cell. When you execute a cell, it will like do the code that's in that cell, and then any output that you've asked it to produce, it will produce it directly afterwards. Kind of for this first one, I'm gonna click the like play button here, and that's gonna run it. And there's actually no output here, so it like didn't do anything. But if I did put output, then it will print it directly below. Okay? So that's how the Jupyter Notebook works. There are some like little tricky caveats that I'm just gonna briefly go over. Again, if you use Jupyter Notebook, I apologize. But if you haven't, you should know that when you like run the cell below, it saves all the variables from the previous one. So like those variables still exist. So if I was to go up here and make a variable called like, test equals high, and then I run this cell, test equals high is like a variable that exists, and I've defined it because it exists in this previous block. And so if I print test here, and then I run it, even though I defined it in the previous cell, like test still exists in the next one. However, right, if I go here and I change the value of high to be by, and then I don't run this cell, if I don't run it, the value doesn't get updated. And so when I run this one again without running the top one, it still prints high. Like I can just run this a bunch and it's gonna say high until I run the one above, which will update the test variable to say by. And when I click this, it says high again. Or by, sorry, correctly, whatever. Do you guys understand, right? You have to do it in order, and if you mess it up, it will yell at you. So it won't yell at you, it will just be wrong. Or it might yell at you about a variable not existing, so like that's frustrating. So make sure you run it in order. And if you edit something up top, rerun the one up top and then everything below. Otherwise it will yell at you. So that is that. Cool. All right, so I'm gonna kind of go over this code here a little bit. Okay, this code up top, this is just imports. So the library we're going to be learning how to use today is called scikit-learn. And the way this notebook thing works, by the way, is that it's not running on your computer. This is a Google-provided server that has all this stuff pre-installed, so you don't have to deal with installing things. And that's why we're using it for this workshop really quick. So, in Python, the way you import stuff, again, I'm assuming you all know basic Python, you just kind of import, from whatever. And the models that we're using, you'll notice they're the ones we just talked about in the workshop, like lecture slides. So we have the linear model, we have the neighbors, that's for KNearest Neighbors, and then we have the tree, and that's for the decision tree. And then we've imported matplotlib for plotting things, and that's how you get the graphs. And then we've got numpy, which is just, it lets you do like fancy 2D arrays, matrices, for those who are familiar with linear algebra. If you're not, don't worry about it. And so, yeah, those are the Python imports. When you run this cell, it just imports these libraries for you. Again, you don't have to install them because it's like a Google server that has everything installed for you automatically. Okay, and that's like what this little check mark is up here too. This is like a check mark that says you're connected to the Google server. So when you click the first one, it'll say connecting to runtime, and it will like do all this stuff. Okay, and then I'm going to go over kind of line by line what this code does, and then I'm going to ask you guys to implement some stuff on your own afterwards. So this up top here, this is me just creating some dummy data. Okay, this data is it's just some points that fall on a 2D plane, and the data processing here stuff. Really, what I've done is I just put them all in a big list, and then I turned it into a table of like x comma y, basically. Okay, so that's like what that gibberish of data x and data y does. It turns it into the x coordinates and the y coordinates, and then I'm just going to plot it with matplotlib, and then I'm going to show the plot. So when I run this cell, you will see that my plot appears. Sorry that it's kind of hard to read, but down here it goes from 0 to 3.5, and the bottom thing here is 2 to 6. So you'll notice that, like, whatever, the points are all here, and they roughly are aligned, right? But they're a little bit noisy, and so we're gonna try and like fit some models to them. So we're gonna start with obviously like a linear model because it looks like a line, so like that would be a good first guess, right? And the way we're gonna do that is I have like defined this linear regression function, okay? And the way this works is it takes in some x values and some y values. So remember, regression is a form of supervised learning. And so when we train our regression model, we need to pass in both the inputs and the correct outputs. So if you remember, this is like y equals mx plus b. X is the inputs of the function, and y is the outputs. So the y's here, they're going to be the correct outputs. We know it's correct because it's literally the y coordinate of this point. Okay? It's literally the y coordinate of this point, so that's like, we know it's correct. That is what the data says. And then we're going to pass it into this function, and we're going to create a model, and the model is going to be a linear model. So model equals linear underscore model, all right? And linear underscore model is the thing I imported from scikit-learn. So I imported that, linear model dot linear regression. That's it. It creates a new linear model, right? And the parameters for this are like gibberish right now because I haven't trained it yet. But it's just a new empty linear model. And once I've created it and I've saved it in this variable called model, I'm going to call model.fit. And what model.fit is going to do is it's going to train my linear model with the inputs and outputs that I've provided. And remember, these are the inputs and the corresponding correct outputs. And so I'm going to train the model, model.fit, right? Remember overfitting and underfitting, we're just fitting the model, okay? And then I'm going to return the model. And so I'm going to run this cell, and it doesn't do anything because this is just a function definition, all right? So I've shown you how to create linear regression. So like basically these 3 lines of code, that's all you need to write linear regression. Like you should be able to leave here now and like get some data and write linear regression, and then it will just work. So all the stuff we talked about, no disgusting math, no yucky logs, none of that. Just these 3 lines of code, you're like good to go, okay? So that's it. There's the linear regression function. And then I'm going to kind of, right here, all I'm doing, like this is the function, and all I'm doing now is I'm just passing in, you can see it passing in data x and data y, and then I'm just plotting it, okay? So literally, all this does is it passes in the x and the y coordinates, like to this function. I'm just calling the function I defined earlier, and then I'm plotting the points, and then I'm going to show you the plotted points, okay? So when I click run on this cell, you guys can do this as well, like follow along hopefully, right? You will see that my linear model has overfit the crap out of this, and that's because this is not a plain linear model. The default model in scikit-learn is a linear model with additional nonlinear transformations, okay? So the reason it's not a straight line is because by default, scikit-learn just assumes that you want like the log linear, for example, right? It's not actually log, but they add some other fancy transformations, and they assume that that's what you want because usually that's what you do want. And so they're giving us this like really, really overfit, like you can see that the line just goes through every single point, right? Bang on, you have predicted every single point with perfect accuracy. And right, this is overfit, but remember, this is overfit to the data that we gave it in, and I never actually made any test data. Like, what I passed in here is I trained it on the training data, and then I told it to predict the training data, and it just like kind of memorized it and spat it back out. So, you know, that's like not what you would normally do. You would also normally make test data that you don't train the model on and then test it on that, but for simplicity's sake, I've not done that. I'm using the same data everywhere, okay? So hopefully that like makes sense. Oh, talking light, right? Yeah. All right, I'm moving this then, if that's the case.
Fine. Before it, just pull it.
All right, thanks. All right, cool. All right, so that's how you do the linear model. Like, does anybody have any questions about that? It's like not too many lines of code, so hopefully it's flowing along pretty quickly. Cool. Yeah, we're just gonna kind of go through the other models then. Right here, we've got a K-nearest neighbors regression. So remember, it's regression because with K-nearest neighbors, you can kind of do 2 different problems. You can either classify something as being like some class, like dog or cat, or you could do regression, where you try and give out a continuous number. Again, the same thing you do if you want to do a classification for the K-nearest neighbors. You just take all the neighbors and they all vote. And if you want to do regression, you take all the neighbors and just average them. So that's just the difference between classification and regression. And so here we are writing a regression function because these are all numbers. They're not classes. They're just numbers. And again, I'm passing in the x and the y. And now notice that I'm also passing in the k, which is the hyperparameter, right? And that's what we want to vary to figure out how good or how overfit or underfit our model is going to be. So that's important. And it's literally the same thing as above, okay? Like these 3 lines of code are, again, very, very simple. Model equals neighbors. So this neighbors thing, it's literally what I imported from scikit-learn. So import neighbors, right? I'm taking the neighbors, and then I'm telling it the type of neighbors algorithm I want is the K-neighbors regressor, okay? So how did I know that was like the name of the function? You just look it up on the documentation. And so, you know, I passed in that the number of neighbors I want is equal to K, and then I told it, hey, fit my model, and then return the model, and it's literally the same as linear regression. So these 3 lines, all you need to do K-nearest neighbors on like any data you want. Okay, so I'm gonna run this function definition. Doesn't do anything, it's just a function. And again, I've done the exact same thing that I did above, where I just took the data, okay, I passed it in through the K-nearest neighbors thing, and then I took the data again, and I just told it to like predict on the same data that I trained it on. All right, and I'm gonna plot that, and you're gonna see a graph. And it looks like this. Remember, this is very much unlike the linear regression with the transformations. Because that had a bunch of transformations, it was like super overfit. This, I told it that the number of neighbors was 2, so it is what it is, right? This would generalize well maybe to like other data, but again on our training data, it's like
What happens if you change to 3?
So yeah, what happens if I change the 2? That's a good question. Let's find out. So we can change the 2 to a 3. Yeah, we can rerun it, and you'll see that you get a different graph here, and yeah, you'll notice that it is kind of worse, right? So that's what I was saying about the hyperparameters. You know, if you want to get actually a super overfit model, as you all know, right? If you overfit a bunch, you can just do k equals 1, and then that will give you very, very overfit, right? And then if I say like how many data points do I have here? 6. So if I do k equals 6, then I'm just gonna get a line, right? Like a really garbage line, actually. So actually, I'm really curious what happens with 5. Will it like? Yeah, perfect, cool, right? So you can see what happens as you vary k. You can try this out for yourself. Like you have the notebook, just feel free to play with the stuff there, and you can also play with like different data if you'd like, right? Like I just defined the data at the top. You can feel free to pass on whatever you like. And then I'm just gonna move on, right? Any questions about KNearest Neighbors, real quick, before I like move on? Yes.
So basically, K-neighbors are basically like an average of like a part of like a group of that like nearest values.
Yeah, it's an average of the group of nearest values. So like when I put in, yeah, let me see if I can plot this in a way that like might actually help you visualize it more. Hold on. What I'm gonna do is just do B star. Okay. So I've changed this plot now from like a line plot to a point plot for the like predictions. Okay. So remember, red is the real data. Okay. Blue is my predictions. So if I turn this into 6 and I run it, like you'll notice, remember, x is the input, y is the output. So what it's doing is for every single x that I give in as an input, it's averaging all of the y values and spitting out the same average for all of them, right? This is what we talked about with KNearest Neighbors, that if you pass in all of the data, you just average it once and you get the same thing no matter what the input is. That's exactly what you're seeing here. It's a straight line that goes all the way across with the same output for every single x input, right? And that's why it looks like a straight line. That's why it looks just like that. And your question was, is it just taking the 5 closest? That's exactly right. So if I change this to 5, like you'll notice that these two bump up a little bit more, and that's because the 5 closest points to like this point right here, they're different from the 5 closest to this one, and so that's why the average is different. Okay.
Yeah.
Cool.
Makes sense.
Yep. Perfect. All right. Any more questions about KNearest Neighbors? Okay. Cool. All right. So the last thing, decision tree. Like I feel like this is getting stale at this point, but it's exactly the same thing again, right? We have the decision tree function here that I've defined. I pass in my x and my y, right? That's the inputs and the outputs that I want to train on. And then this time, instead of k, I'm passing in d. Anyone want to? What's the parameter for a decision tree? Anyone? Shout it out. What's the d stand for? Depth. Yeah, nice. All right, cool. So this is the depth. Same thing. Model equals tree dot decision tree regressor, blah blah blah. And so up here I've imported tree, so that's where that's coming from. Right, tree dot decision tree regressor. Again, we're doing a regression problem. Like our outputs are numbers; they're not classes. And so the criteria on here, this I have put as MSE. So if you guys remember, anybody, what was MSE? Let's see, what does it stand for? Someone?
Shout it out.
Yeah. What? Louder.
Square means thing?
Yes. Is that right? It stands for mean squared error. Okay? And that is exactly the same thing when we were doing the linear regression problem. We talked about the error being computed by this, like, taking the real output and the predicted output, right? And subtracting the two, squaring it, and then summing all of those up and averaging. So that's what's called mean squared error. And that is the criterion, right? So like that's a parameter that you have to pass in to this function. When you want to do the decision tree, it needs to know whether you want to compute using the mean squared error as your error function, right? Like what is the type of error you would like to compute? And then it's going to say, max depth equals d. That's what we passed in earlier. Then you're going to do model.fit and return the model. It's very much the same as before. And as a side kind of tangent, remember earlier I had told you that other than the square, like what was the other thing you could do? Does anybody remember? There was like one other way that you could compute the error that's not squaring.
Absolute value.
Yes, absolute value, perfect. So if you want to do absolute value, just to kind of see what happens, you can change this MSE to MAE, and that's mean absolute value error. Okay? And that's like, now it's super easy, right? Like you don't have to write the absolute value, you don't have to like rewrite the function, you're not writing the error function, you're just telling it, hey, use MSE or use MAE, okay? And that is how scikit-learn works. So that's the model. I'm gonna do mine with MSE and MAE, and I'm gonna see if there's any difference. I actually think on this data set there's not very much of a difference, but we will run it and see anyway. Yeah. Okay. So cool. So you guys can see that, like, with the mean absolute error, it's the same. It's the same kind of shtick as before. I have a depth of 3, so I'm basically overfitting a lot to this data. If I change this to MSE, I think it's basically the same if I remember correctly, but could be wrong. Yeah, you can see it doesn't really make a difference, right? There are reasons mathematically why you might want to choose one over the other. There are certain types of data where it will make a difference, but in this case it doesn't. I think really specifically, like, it's not actually that unintuitive, right, to think about it. Basically, when you square something, that means that things that are farther away, they like have more weight, basically, right? When you square it, like, they just become more than what they already were. Whereas if you take the absolute value, you're only getting rid of the negative sign, and so stuff that's far away doesn't get even farther away from like what the prediction was, right? So the distance is less, because that's the thing inside the square or inside the absolute value. It's a distance. Remember that.
Yeah, and that means that if you're using mean squared error, you are heavily weighting points that are very far away from your sort of what you're probably going to guess, which means that you might fit to sort of the outliers, which is not something you necessarily want if you've got a noisy data set that has a lot of outliers. And so sort of like mean squared error might work better than mean absolute error locally, but if you've got a data set with a lot of outliers, then it's going to cause problems. So sort of like graphing the data, looking at it, maybe even doing some kind of computation to see how bad the outliers are might help you make that kind of decision.
Yeah, that's exactly correct. That's exactly correct. And remember, like, I am here just kind of trying them both and see what happens. And like, I did mention that trial and error is a good way to do things in machine learning, and I still stand by that. Trial and error is very excellent. You should always be doing trial and error when you're doing an ML you're trying to solve a problem with machine learning. However, what you guys, again, have to remember is that the reason why we're stressing this, like, theory so much, right? Like, I literally spent an hour not doing any code. And the reason for that, right, is because machine learning oftentimes uses very large data sets, and it takes a really long time to compute the models. So, like, you might put in millions of points of data and ask it to train, like, a K-Nearest Neighbors model, and it might take a whole week just to, like, figure out, or K-Nearest Neighbors is a really bad example because you don't train it. Sorry, but like a decision tree, right? You might be like, hey, train me a decision tree on this like 2 billion point data set. And then your computer is just chugging for a week. And so it's kind of hard to experiment when it takes you a whole week to train your model and get some results. And then you're like, oh, but like what if I tweak this a little bit? Like, will it be better? So then you tweak it, and then you have to wait a whole other week. Like, that sucks. Nobody wants to wait 2 weeks just to see whether you should use MSE or MAE, right? Like, that's why we're trying to get you guys to think about the theory, because if you understand why, then you wouldn't have to do that. You would save 2 whole weeks of sitting around by just thinking about your data, plotting the outliers, and remembering that, hey, if I have outliers, maybe I should use the absolute value instead of the square, and then you pick the right one right off the bat, and you just saved yourself a whole week. So that's like why we're stressing it, okay? Yeah?
Then in which case should we choose the square over the absolute value?
I would say in general, because it weights things farther away more, if you don't have outliers, it's probably going to be slightly better.
Yeah.
So it's sort of like the default. Like mean squared error is the default.
Yeah.
It only gets messed up if you've got outliers.
Yeah, mean squared error works better in general, but if you have like lots of outliers that are like very far away, then mean squared error might get messed up, and then you may choose to switch to mean absolute error. But like again, you can consider choosing that error function as like another hyperparameter. It's just another parameter to the ML model that you just like have to choose and come up with. And there's no like necessarily correct answer. There's just like things that might be better, and it depends on your data. And so you, the user, you have to specify it. Like that slide that said that's user specified, like that's not my line. There's ML professors at this university will tell you that's user specified, because that's exactly what they mean. It's something you have to choose based on your data and your application and like what you're trying to do. And no one can just tell you the answer. So that's that. All right, so yeah.
Drop the depth.
Oh yeah, I should drop the depth. So why don't I try that? We're using MSE, and we're gonna change the depth to be like 1, no 2. It was 3, right? So let's make it 2.
It was 3.
Yeah. All right. Cool. So like you can see that it's less overfit now with a depth of 2. We're kind of approximating, but not as well. And again, if you drop it to 1, we're gonna get something like this. This is interesting because it's like it's not. It doesn't look like it's a completely incorrect approximation, right? But it's like it's not right either. Like you could argue that this is that this is the correct approximation over like a line, perhaps. I don't know. Again, depends on your data, whether or not this is like the kind of trend you're hoping to uncover. All right, so we have about 15 minutes left, which is not necessarily enough time to do what I said we were running fast and we would have extra time, and then I totally lied about that. So I'm sorry. It's probably because I went on all those tangents. But so we have about 15 minutes left. The activity I'm going to have you guys do next, if you want to, and if you are willing to is there something after this?
I think it's lunch.
Okay, cool. So yeah, there's nothing scheduled in this room afterwards. So if you want to stay and keep working on the activity, you're more than welcome to. That's why I have Shane and Kevin here to help me. They're going to help walk around and help you guys in this next activity. I promised that we would talk about deploying machine learning models to your hacks, right? So I want you to go away from this workshop being able to train a model and then use it in your website. No joke, use it in your website, right? So we're going to talk about how to do that right now. And more importantly, what I'm going to have you guys do is I have actually created, not one of the, yeah, me, I have created. Chris has created. Chris, one of the other TAs who is not here, unfortunately, right now, has created this ML workshop starter. So I'm going to post the link to this in Slack, okay? So I'm going to ask you guys all to go to this repository, all right? And I'm going to ask you to, again, clone this onto your computer, download it, whatever. I guess basic Git, just Git clone, get it on the computer somewhere, all right? And take a look at it. And so what this does, all right, it's kind of the starter code. And the real gist of it, the only thing you have to really take into account, there's some data, okay? It is diabetes-related data about people's age, their gender, their body mass index, and then their blood pressure. And as a result of that, you're trying to predict their risk for diabetes or something like that, okay? So that's this data. It's in this text file here. And then also, we have some other data, but I don't think we're actually using that, so we'll ignore it. And then this templates folder, it contains a really basic website. So this is HTML, and it's the most simple website you've ever seen. And then same thing with this, another HTML file, literally 4 lines. Okay, so this is the most basic website you have ever seen in your whole life. But that's okay, because it's a website, and it's gonna work with your model, which is pretty sick. So the way we're gonna do that is I'm going to show you guys this file, but I'm not actually going to write any of the code up here. You're going to write it. You guys are going to write it, okay? So let me give you the instructions, and then we'll come around and help you guys. If you install things, we'll help you do all that. Because you will need to install scikit-learn, right? Those packages that were automatically installed for you on the Colab notebook, you're going to have to do that locally. So what we're using here is called Flask, and Flask is a really basic web server in Python. And what it lets you do is it lets you host a website from your computer locally. And so when you run the Flask server, all it does is it goes to your local host, your computer's IP address, and on a port it will just display a website. Okay? And it's more than just a static website. There's also a whole server behind that website, and that server is your computer that lets you do some computation when users click things on the website. And that's really important. So what we're going to do with this file, right, is there's this Flask kind of stuff. At the top, it's just imports, so we're going to ignore these Flask imports. They're just imports. And then we have these scikit-learn imports, and you'll notice the only one implemented for you is the linear regression. That's intentional, because you guys are going to write the KNearest Neighbors and the decision tree by yourself. Okay, that's what you're going to do. The linear regression is here for you as an example. And I've shown you how to do the KNN and the decision tree in the notebook, so you should be copying that format, looking at those functions, so on. Right? So yeah, we import pandas, we import NumPy, just some data processing stuff, really basic. We're going to load the data, and you'll notice we're loading the diabetes data from this diabetes text file. And then we're going to train our model. And if you look at this train model thing, I swear to God, this is identical to the notebook. The names might be different, but if you look closely, it's exactly the same thing as what we had in the notebook. You have this regression model, regression.fit x, y, return the model. That's it. Okay? And then, this is it. This right here is all you need to deploy your model to a website. We have created a Flask server, and the URL for your prediction thing is just going to be /predict. So your URL, in your case, right, when you run this, it's gonna be localhost. So localhost, like port 8080, whatever, on your computer, it's running that. You go to /predict, and you just send it these inputs via the HTML page that you saw earlier. You're gonna type them in. Alright, and you can try this. You can like clone this, and if you're able to run it, so you have the stuff installed. When you run python main.py and then go to localhost 8080, this website works right now, right off the bat. You'll be able to input via the form on the website. You'll be able to input your age, sex, BMI, and blood pressure, and then we run model.predict on those inputs that came from the website. Right, like this is the inputs. You can see it's coming from request.form, and that's like the form on the website. And then we're gonna pass it into the prediction, and then we're just gonna like spit out the output. And then there's a main function here that just tells you like run main, and that's it. There's like no more than maybe 10 lines of code that are actually relevant. And now you have created a model, you trained the model, and then you can let other people like use your model on a website. Okay, that's pretty wild. So you don't have to write all this code yourself. Again, we provided it for you. But what I am going to ask you to do, if you want to, because I know we're slowly running out of time, okay? If you want to, as an exercise, implement KNearest Neighbors and the decision tree with whatever hyperparameters you want. Like, don't worry about over and underfitting. Just worry about writing it in this thing and having it run on the website. Okay? So yeah, I would recommend you like download this repository and then like start installing the stuff. So if you're familiar with Python, if you have Anaconda, you should do conda install. You don't actually have to. Conda will come with all of this. So if you have Anaconda, you don't have to do anything. And if you have not Anaconda, or you don't know what I'm talking about with Anaconda, then you have Python installed, then you should do pip install like NumPy, pip install pandas, and pip install scikit-learn. And then if you don't have Python installed, you should like raise your hand now so that we can come around and help you. Okay? It's like 1, 2, like 3 people. Oh no, questions. The pip commands? Yeah, absolutely. Great question.
Just gonna write them.
Yep.
You also they need Git, right?
Yeah, I mean, I'm assuming you already have Git. Pip install the P. I don't remember the scikit-learn one.
sklearn.
Is it sklearn or scikit-learn? It is sklearn. Okay, sick. Those are the pip commands you need for those of you who are using pip. If you're using Anaconda, like, know what Anaconda is, but you don't have to install it, right?
Pretty sure what Anaconda is.
Yeah, those people are. Alright, is there anybody who needs help installing Python? Raise your hand. Do you have a question?
I just have some I want some help.
You want some help? Okay, alright, yeah, we'll get there in a second. Anyone needs to install Python? Keep your hands raised if you need to install Python. Let's go.
Why don't we gather? You wanna just
Oh, yeah,
gather?
actually, if you need to install Python, come up here. Come up here. When you do that, Shane and I go down here.
Is it particular Python?
What I just, if they don't have any Python, install conda. Right, do mini class.
I'm gonna ask.
What? No, you.
No, just let him do whatever he wants.
Yeah.
Just wanna make sure we're fine.
What's up?
Okay, just let him do whatever he wants.
Stick with it.